In this session, we will study principle of operation of three-phase induction motor. Induction motor works on the principle of electromagnetic induction, hence it is known as induction motor. We know that the induction motor consists of two parts, stator and rotor. In the stator we have three windings displaced 120 degree electrical. These three windings are connected to three-phase supply. Whereas in the rotor circuit you have got rotor conductors. On either side of the rotor conductors they are short circuited. When a three-phase supply is given to the stator winding, the alternating current will start flowing in all the three windings. They are displaced by 120 degree with the equal magnitude. Also we know that whenever there is a current is flowing through a conductor or a coil, it is producing its own magnetic field. Therefore, these three windings, they are producing flux phi 1, phi 2 and the phi 3. These fluxes also they are alternating in the nature. When these three fluxes are interacting each other, they are producing a resultant flux having a magnitude of 1.5 times the maximum value of the flux. At the same time, it will rotate with a speed of synchronous, that is, it is given by 120 f by p, where f is the supply frequency, the p is the number of poles, where ns is called as the synchronous speed. It is synchronous speed of a rotating magnetic field. These are the points you can see once again. The balanced three-phase stator winding, that is mechanically displaced 120 degree from each other, fed by the balanced three-phase source. When the supply is given, the current starts flowing. Because of the current in the coil, they are producing the magnetic field. Then ultimately, interaction of all the three fields, a rotating magnetic field with a constant magnitude is produced and rotating with a speed of ns is equal to 120 f by p. That we'll see. Here we have got a stator, we have got a rotor conductors. Here we are having three stator winding, and these three stator winding are excited by three-phase supply. These are connected to three-phase supply. When a three-phase supply is given to these three windings, the currents I1, I2 and I3 will flow in their respective windings. Because of flow of these currents, they are producing their own magnetic flux. That is, the phi 1, it is due to phi 1, I1, and phi 2, it is due to I2, and the phi 3 flux is because of the I3. Therefore, there are three fluxes they are producing and they are interacting. Because of the interaction of all these three fluxes, a resultant flux will produce and it is rotating with a speed of ns is equal to 120 f by p. Then the principle of operation of a induction motor is very simple. Once again you can see the diagram here. When there is a rotating magnetic field is producing here, at the time starting the rotor is at rest or a standstill. At the same time, a rotating magnetic field is which is sweeping the rotor conductors. According to Faraday's laws of electromagnetic induction, whenever the flux cut the conductors, there is an induced voltage in the rotor conductors. Because the flux is rotating, the conductors are stationary. Because of that, there is an induced voltage in this rotor conductors. At the same time, we know that these rotor conductors are short circuited on either side. Therefore, the current starts flowing in the rotor conductors. Then you can recall the principle of operation of a motor that states that whenever the current carrying conductor is placed under a magnetic field, the force is exerted on the rotor. See here, because of the rotating magnetic field, there is an induced voltage in the rotor conductors. rotor conductors are short circuited. Because of that, the current starts flowing in the rotor conductors. Then the current is flowing in the rotor conductors. There is a flux by all the three windings. Then current carrying conductor is placed under a magnetic field. Because of that, the force is exerted on this rotor conductor, thereby the rotor start rotating, thereby you are getting a mechanical energy. That is, the three-phase supply, whatever the electrical energy you are giving to the stator, that is converted into a rotating the mechanical energy in the form of a rotation. The same thing we will see in the next slide. That is, the rotating magnetic field cuts the rotor windings and produces an induced voltage in the rotor windings. Because of the flux is cutting the conductors, because of the Faraday's laws of electromagnetic induction, there is a induced voltage in the rotor conductors. And we know that rotor windings are short circuited for both squirrel cage as well as wound rotor. Then an induced current start flowing in the rotor windings. When the current carrying conductor is put in the magnetic field, a force is produced on it. It is a principle of a motor. Thus, the force is exerted on the rotor conductors. The direction of the force, once again, it is determined by the Fleming's left hand rule. The force acting on these conductors is in the same direction, that of direction of rotating magnetic field. That is, rotor start rotating in the same direction as the rotating magnetic field. That is, the principle of operation of the induction motor is also put in a different words. That is, we know that Lenz's law. What the Lenz's law states? That is, it is opposing very cause of producing it. The cause of producing the induced voltage or the induced current in the rotor conductors is because of a rotating magnetic field. Then it is trying to catch up that particular speed so that it is opposing. Thereby the rotor start rotating. That is another way of putting the principle of operation of a three-phase induction motor. That is, only these things you can remember. That is, whenever three-phase supply is given to the stator winding, then there is a rotating magnetic field is producing the air gap that cuts the rotor conductors. Because of electromagnetic induction, there is an induced voltage in the rotor conductors. Also, we know that the rotor conductors are short circuited on either side. Therefore, the current start flowing in the rotor conductors. And the situation arises, that is, the current carrying conductor is placed under a magnetic field. Because of the motoring action, then the current carrying conductor, if you are placing under a magnetic field, there is a force is exerted. Thereby there is a conversion of electrical energy into a mechanical energy. The rotor start rotating in the same direction as the rotating magnetic field. Then, what is the speed of the induction motor? At what speed the rotor of the induction motor will rotate? Whether it is equivalent to the synchronous speed or it is less than the synchronous speed. That question arises. Here we are raising two different questions here. At what speed will the induction motor run? Definitely the speed of the rotor of the induction motor, which is always less than the synchronous speed. Can the induction motor run at the synchronous speed? No, it never run with the synchronous speed. If it runs with the synchronous speed, there is no relative motion between the rotor and the rotating magnetic field. Thereby there is no induced voltage. If there is no induced voltage, there is no current. Therefore, there will not be any torque is producing in the three-phase induction motor. Therefore, the induction motor will run less than the synchronous speed. If the rotor runs at the synchronous speed, which is the same speed of the rotating magnetic field, then what happens? Then the rotor will appear stationary to the rotating magnetic field, and the rotating magnetic field will not cut the rotor. Therefore, so no induced current will flow and no torque is generated. Therefore, when the speed falls, the rotating magnetic field, then there is a relative motion between the rotating magnetic field and the rotor, then there is a induced voltage and there is a current, then there is a torque is producing. Therefore, the speed of the induction motor or rotating magnetic field is ns, that is what you are calling as synchronous speed, that is synchronous speed of rotating magnetic field. Whereas the speed of the rotor is represented by n. These ns and n, they are measured in terms of rpm, revolutions per the minute. Definitely the n is the less than ns. Induction motor speed, that is, we know that we have got two different speed. One is the rotating magnetic speed, that is rotating with a synchronous speed of ns. At the same time, the rotor will also rotating with a speed of n rpm. There is a difference between the rotating magnetic field and the rotor speed. Then the difference between these two speeds is called as slip speed, that is represented by n slip. That is, it is a difference between the synchronous speed and the rotor speed, that is called as the slip speed. Once again, this is also measured in terms of rpm. Then we are defining the slip. The slip is defined as, it is a very simple, it is a ratio of slip speed to the synchronous speed. It is a ratio of slip speed to the synchronous speed, because we are expressing the slip speed with a reference to the synchronous speed, then it is called as the slip. The slip is equal to ns minus n divided by ns, it is called as the fractional slip. If you want this slip as a percentage, just you have to multiply with 100. Means the slip is the difference between ns and n divided by ns. It is one of the figure of merit of a induction motor, that is, the slip is as minimum as possible, so that the difference between ns and n is less. Means whenever the induction motor is loading, the drop in the speed is less, so that the slip is well within the limit. Usually for a standard machines, the slip of the induction motor is less than 3%. Then if you are observing here, what is the slip at two different cases, when n is equal to 0, when n is equal to ns. What do you mean by n is equal to 0? N is equal to 0 corresponding to at the time of starting. At the time of starting, the speed of the induction motor is 0. At the time of starting, the slip is n is equal to 0, therefore it is ns by n, therefore slip is equal to 1. Then if the speed of the machine is synchronous speed, in that case ns minus n is 0, therefore slip is 0. There is no relative motion between the rotating magnetic field and the rotor. Okay, that is the case, that is slip is 0 when n is equal to ns, when slip is equal to 1 when the n is equal to 0. Therefore we have got, you want to express the speed in terms of slip and the synchronous speed. Once again I am taking the relation s is equal to ns minus n divided by ns. Then from this I want to determine what you mean by the rotor speed in terms of slip and the synchronous speed. Just I am cross multiplying here. What I am getting is s into ns is equal to ns into n. Then I am rearranging the terms. That is, I am transferring n to the left hand side, s ns to the right hand side. Then what I am getting is, it is ns minus s ns minus n. If it is transferring to the left hand side, what you are getting is plus n. In these two terms, I have got a ns as a common, therefore I will take ns as a common. Then I will express the speed of the rotor of an induction motor is 1 minus s times ns. There are three important equations we are using here. One is for a synchronous speed, ns, that is given by 120 f by p. The other one is the slip, the third one is the rotor speed. Then I want to establish a relation between the stator frequency and the rotor frequency. There is a difference between the stator frequency and the rotor frequency. The stator frequency means it is the frequency of the supply voltage. But the frequency of the rotor is different because the induced voltage is inducing in the rotor conductors because of relative speed, that is ns minus n. Therefore, the frequency of the rotor voltage or a current is differ than the frequency of the stator. I'll start with the stator frequency. That is given by straight away f is equal to Pns by 120. That is, f is the supply frequency. It is a supply frequency or it is a stator frequency. It is given by Pns by 120 f. Because of this frequency, we know that a rotating magnetic field is producing with a speed of ns. That is why f is equal to Pns by 120. Then I will take a rotor frequency. The rotor frequency is because of the slip speed, that is ns minus n. Therefore, the similar equation Pn by 120 equation I am using, instead of ns I am replacing that by ns by n, because here there is a induced voltage because of slip speed. Therefore, Fr is equal to P into bracket ns minus n divided by 120. Then I am dividing Fr by F. Then what I am taking a ratio of Fr by F. Then what I am getting is P into bracket ns minus n divided by 120 divided by Pns by 120. The 120 Pp get cancelled. Then what we are getting as in the numerator ns minus n, and in the denominator what I am getting is ns. That is, Fr by F is equal to ns minus n divided by ns. Then we know that the ns minus n divided by ns is nothing but the slip. Therefore, I am replacing this by s. Therefore, Fr by F is equal to s, where Fr is the rotor frequency, F is the stator frequency. Therefore, if we want to express Fr, the Fr in terms of F, that is slip times the stator frequency. That is, the rotor frequency is s times the stator frequency. This is important relations what you are deriving for the rotor frequency. Based on these equations, in the next session we will solve some of the example on the slip, rotor frequency, stator frequency and the synchronous speed.